Pilot G2s or whatever, those are even smoother in my opinion, but they smear easily after you write them, so those dry really quickly.
And then medium point, I assume.
I use the fine point, the 0.5 needle tip. It gives you a little bit more precision, like on looking at what you're writing, but it's not really necessary if you're just like putting check marks and like numbers on papers and stuff.
Rarely doing high precision
Yeah.
stuff. Though I have found I was practicing learning how to draw people for 2 years. I need to pick it back up again. And I got to the point where I realized I was having difficulty drawing small versions. I mean, if I'm drawing a face on an 8.5 by 11, no problem.
Mhm.
Oh well, give me some time and I can do it. But if I wanted to do a whole body on an 8.5 by 11, I would have it smaller. And it eventually dawned on me that I can't do it easily or well because to get the detail,
Yep.
I need a much finer point than anything I have.
And that's in digital artwork. They use like really high resolution to begin with, so you can like shrink it down later to get all that detail. Or even like old painting, like they're doing like really realistic paintings, like a lot of the really good ones that look super realistic and like really big.
I don't think they have to be.
No, they don't have to be. They're really good artists.
Well, okay.
Figure
But
drawing.
I am the watered down talent of watered down talent.
Figure drawing is really hard anyway, so.
All right. Use this as a transition into physics. Are there any questions?
Not yet.
Then let us continue on with magnetism. So we've realized that there's a North Pole and South Pole. Not necessarily, don't consider it plus or minus. So let's connect. Sorry, hangnail that something broke loose.
Yes.
All right. So let's talk about the connection between the stuff that we have been doing over the past however long, 2 months, and magnetism. So first off, to create a magnetic field, you need a moving charge. And I think we got to that last time.
And there's one other way to do it, but you never told us how.
Yeah.
Oh, that's
Or
right.
dot
That's
dot
right.
dot.
Yeah. We'll get to that. That's basically Maxwell's contribution to Maxwell's equations. And again, I probably mentioned this before. Maxwell's equations, Maxwell did not call them that. He actually seemed to be a physicist with some humility. For rare reason. All right, so B is used for a magnetic field. Historically, I think it came down to whoever was writing the paper who established that. Needed letters and used A for the first thing he needed, B for the next thing, C, and so forth. So B stuck. You will find some textbooks that won't use B, they'll use H, and there is a relationship between B and H, but most textbooks, especially starting out, use B for magnetic field. It's the more advanced ones that suddenly say, well, B is really magnetic flux density. H is magnetic field. Sure, whatever. All right, so more specifically, and we introduce the second physics equation of the course, first one being Coulomb's law. We have, this one's not quite as nice. There's no real quick plug and chug, at least at this level. And I am looking at my notes just to make sure I don't get something off. U naught over 4 pi. dq v cross r All right, this is known as the Biot-Savart, spelled Biot-Savart law. I did find one textbook that said it rhymes with neo-bizarre. So it's the Biot-Savart law. There are 4 forms of it. This is one of them. So the first one just deals with, I gotta move in charge. The first 2. The second 2 deal with if I have a current. So I've got a steady flow of moving charges. To put it in the second form, it's very simple. The fact that if I have any vector, well, all vectors have a magnitude and a direction. So what I'm gonna do is I'm just gonna take that and that's the magnitude times the direction. So, and you can do this with any vector, that it's equal to the magnitude in whatever direction it's pointing in. What that does over here is I can substitute that in for r there, and I get mu sub naught over 4 pi dq v cross r hat over r cubed. That r cancels out with one of those, and so we are left with mu sub naught over 4 pi dq v cross r hat over r squared. So they mean the exact same thing. Use whichever form is more convenient. Traditionally, when deriving something, I use this one right here, or the current form of it. Questions up to you?
Oh, your second R is an R hat this time.
Yes.
Okay. Yeah, I was wondering how you can have like 2 equivalents with this R in the denominator.
Yeah, and that's the difference. Some textbooks will present one and not the other, or both. All right, so we have velocity times the cross, doing a cross product with the radial vector, or down here, radial unit vector. What is velocity?
Change in position
If you're stopping there, I would say no.
over time.
Okay, thank you. Or calculus based too. What letter are you used to for position?
As.
The letter that you use for position?
As.
You said
Or as, yeah.
As.
S. Okay, sorry. Didn't quite hear that sound at the end. All right, so this, whichever form, I'll take this one, is also equal to mu naught over 4 pi dq times ds dt cross r over r squared. So I'm just going to shift that denominator dt over 1, and so I get mu naught over 4 pi dq dt ds cross r hat over r squared. And what is dq dt?
I should know this.
Yes. If it helps, you can think about the units.
Current.
Yes, it's current. So mu naught over 4 pi naught over 4 pi current times ds cross r hat from r squared. Or, so that's the third form of this equation. And then sort of reversing what we did over there, we also have mu sub naught over 4 pi times the current ds cross r vector over r cubed. So those are the 4 forms that we have for differential of the magnetic field. So we got that one, that one, that one, that one. And again, I prefer the R vector instead of R hat, just because it's, in my mind, simpler. And of course, we're about to do an example. So let's start out with, I have a current flowing to the right. And what I want to know is, what is the magnetic field at that point right there? We will make this distance R. Yeah, I'm using R way too much. Let's make that L. So my current is going to the right. I have this ds right here, and that would be the direction of the positive charge flow, or opposite the direction of the negative charge flow. So ds in this particular case is going to be to the right. As with anything where I've got a differential involved, I'm just going to start out with taking a small piece of it, ds. This is my vector R. That is some distance x. And that'll be 0 there. So, right off the bat, assume traditional I hat, J hat. Well, if I'm going to plug into that, I need to figure out some stuff. So, ds is some differential, some tiny amount of length pointing to the right. So that's just going to be dx I hat. Assuming that's an x-axis. R vector, well, it's from this point to that point right there, so it's x I hat plus L j hat. And R itself, well, that's the hypotenuse of this triangle, so it's the square root of x squared plus, it's supposed to be a 2, x squared plus L squared. So dramatic pause for people to ask questions or point out mistakes. All right, let's do a little calculus. So we have dV is equal to mu naught over 4 pi times my current times, instead of ds, dx I hat cross R, which is x I hat plus L j hat, divided by, ooh, my x's and the cross look the same, so I know, I'm gonna make my x's fancier here. Ooh. Perfect.
Very fancy.
That's right. Over x squared plus L squared to the 3 halves. Obviously, I have a differential on both sides. We're going to need to do an integral. Let's point out one thing. Mu sub naught. I don't think I covered mu sub naught yet. There's even a video I have where I say do not confuse these mu's, because mu shows up quite a bit. Mu sub, if you think of epsilon sub naught as the permittivity of free space, where it basically, if I have a medium, how's that medium affected by an electric field? This is the magnetic equivalent. So if I have a medium, how is that affected by a magnetic field? And mu sub naught would just be the permeability of free space, as opposed to the permittivity. It'd be really nice if they'd come out with words that were far more distinct. Permeability of free space. It has the units of, well, actually, the units will just be the value. mu sub naught is a constant, and that is equal to 4 pi times 10 to the negative 7th Tesla meters per ampere. Convenient way the 4 pi is going to cancel out.
How convenient.
So it's just like epsilon naught, only it's for relation to magnetism instead
Yes.
of electricity.
Yeah. Eventually, we'll get into a connection between mu sub naught and epsilon sub naught, but not yet. So I'm left with 10 to the negative 7. Well, nah, let's not put numbers in yet. That's spoiling it. Mu sub naught over 4 pi times my current. And now I have to figure out what this mess is here. We've got a cross product. How do you do cross products?
Determinant.
Okay, that's one way. So it would be
I mean, you don't have
dx
to.
0, 0, x L 0, oh, no, sorry. I hat, J hat, K hat. There we go.
Do you have a better way, like, that you would rather do?
Just go ahead and multiply them. Do you know, you can, so if we distribute, then we have x dx I hat cross I hat plus L dx I hat cross J hat. Order does matter, I hat cross J hat, it's not the same as J hat cross I hat. I hat cross I hat. Is that a, what?
Just I squared.
No. What is it? 0.
It's just
It-
one.
No, it's 0. Okay. All right, so let's talk a little bit about cross products. When doing cross products, you're multiplying perpendicular components. So if I have vector A and vector B, and I'm doing A cross B, I can break A up into components. And if I'm doing a dot product, I'm multiplying this length times B, times the length of B. If I'm doing a cross product, I'm multiplying this length times B, this bit right here. If that angle is theta, this length would be A sine theta. And so the magnitude of a cross product is going to be A, B sine theta, as opposed to the dot product, which would be A, B cosine theta.
So you said first, dot product was what, A and?
Would be, if I'm doing a dot product, I'm multiplying the parallel parts, so A cosine theta. So I'm multiplying that times the length of B,
Oh, okay.
or magnitude of B. That's a dot product. Cross product would multiply the perpendicular parts. So if I have two vectors that are perpendicular to each other, theta is pi over 2, and the sine of pi over 2 is 1, so it just is A times B. If I'm multiplying two that are in the same direction, my angle 0, this whole thing is 0, it all goes away. So over here, I'm multiplying the perpendicular parts, which is the I hat and the J hat. So now, comes into, it is a cross product, it is a vector product. The answer is a vector. So what is the direction? If I have A cross B, one of the many right-hand rules, A is in that direction, B is in that direction. You take your right hand, do we have any left-handed people in here? Okay. So I don't have to go into the dominant hand versus right hand thing. All right. So you put your hand in the direction of the first vector. You want your, so I basically have 360 degrees of options at this point. I want my fingers, these fingers right here, when they bend, to bend the shortest way to the second vector. Well, B is going that way, so I bend them like that. My thumb points in the direction of the cross product. So A cross B in this situation would produce a vector pointing into the board. If I did B cross A, I put my hand in the direction of B, and I want my fingers to curl towards A, my thumb points out. So A cross B is the direct opposite direction from B cross A. The commutative property does not hold for cross products.
Or matrices in general.
Yep. So in this particular case, so then we'll take it to the next step, because what is I cross J? In a right-handed coordinate system, I cross J equals K. It is assumed we are dealing with a right-handed coordinate system unless it is explicitly stated otherwise. Although in a lot of tests I explicitly state it's a right-handed coordinate system. Matter of fact, that is my most watched video, is the video on right-handed coordinate systems. 14,000 views, something like that. Wow. Still shocks me.
YouTube things.
I'm guessing if you do I cross K hat, it would just be J.
And then, so, since I cross J, if I think of I to the right, and J up, I cross J is K, so K is coming out of the board. And I cross